Hello, linear algebra student. This video is for chapter 4.3, linear independent set basis. So we continue with vector space that we introduced in 4.1 and subspaces in a vector space. So these vector space consist of vectors, and we want to introduce a special concept called basis that can actually span that subspace or vector space. And later on, we'll talk about the definition. Definition of a basis is a linear independent set, and it would span that particular subspace or the whole vector space. And now in 4.1, the vector space that we introduce are not just Rn, right? But vectors that include polynomials or anything that satisfy the 10 axiom. And for subspace, it would be anything that satisfy the 3 axioms in a vector space. So for a vector space, we haven't, for this general definition of vector space, we actually haven't determined what is called by linear independence, although in Rn vectors, we did define it in 1.7. But so we're just going to redefine it one more time. So we'll say I have a set V1 to Vp, and we call this set linear independence if the only way you can combine them together using the weights C1, C2, C3 is equal to 0. Is the only way is if all the weights are 0. So very similar to Rn. In Rn, we say if the only way we can solve this vector equation is the trivial solution, then they are linear independent, right? So it's the same thing. And then the set will be dependent if the equation has a non-trivial solution. That means you can find some linear combination of them equal to 0, which is not or 0. And a theorem for which is which is the same as what we talk about in 1.7. That is, if you have one vector that is a linear combination of another set of vector in the sets, then this whole set is dependent because you can actually just then find this sets of non-zero C1, C2, and CP. So let's do an example to illustrate how this works for non-Rn. In Rn, we talk about this in 1.7. So this is actually just the same as what we talk about in 1.7 if you are considering the subspace of Rn. For non-Rn, such as a polynomial, let's check how to determine if things are linear independent and dependent. So for example, I have a set of 3 vectors, P1, which is 1, P2 is t, this third one is 3 minus t. So there are 3 different polynomial. Can we see if they are linear independent or dependent? We don't have this concept when we deal with algebra, right, for linear dependence, but because they are objects in a vector space, or actually each one of them are called vector in a vector space. So we'll discuss this concept of linear independence. So obviously you can see that P3 equal to 3 minus t is actually 3p1 minus p2, right? So by theorem 4, theorem 4 said that if one of them is a linear combination of the other one, so P3 is a linear combination of P1 and P2, so they are P2, so this set is dependent, right? So long as you can find some linear combination within them, then they're dependent. They cannot be independent. So by theorem 4 here. Another one, it is this set is 1t squared. By inspection, you can tell that this must be independent because there's no way you can add 1 and t become t squared. It's never possible, right? So we can write this out. We can write C1 times 1 plus C2 times t plus C3 times t squared is equal to 0. Is it possible to get C1, C2, C3 that is non-zero to make this happen? By inspection is not, right? By inspection, why? because this T is not a particular solution. You're not solving solution. T is C1, C2, C3 must be 0 for all T. Because it is a polynomial, that means it satisfies all real number T, right? So if you really want to prove it, so this is actually quite sufficient. But if you really want to prove it, you can actually set T equal to 0, T equal to 1, because T can be any number, right? So plug into this to see what happens. So pretend that we can actually find C1, C2, C3 to do that. Then I have C1 plus 0, C2 plus 0, C3 equal to 0. C1 plus C2, 1 C2 and 1 C3 equal to 0. When T is equal to 2, then C1 plus 2 C2 plus 4 C3 equal to 0. And so we would do just as if you are solving a homogeneous solution for C1, C2, C3, 1, 0, 0, 1, 1, 1, 1, 2, 4, 0, 0, 0. And reduce row echelon. Did I do it already? I think I have it here, right? So this is the one. If I reduce row echelon of H, the only solution is the trivial solution. 0, 1, 0, 0, 0, 0, 0, 0, 0, right? So C1, C2, C3 equals 0. So the conclusion is no place to write. So this must be independent. These sets independent. Where am I? Oh, okay, I jumped down. So it must be independent sets. Not this set, but this set. This is an independent set. Okay, so that's how you prove it instead of just like you say by inspection is kind of strange. Then for RN, so when you do the homework, there are actually a lot of the homework question are an RN back to RN. So do you still remember in 1.7 we have these two theorem? How do I know if a set of Rn vectors are linear independent? Is you put them into columns of matrix A, and they are linear independent if Ax equal to 0 has only the trivial solution. That means there's no free variable. And also, if Ax equal to 0 has a non-trivial solution, then it would has a free variable. So you want to make sure that all prefix columns, there's no free variable. That means all prefix columns has a prefix position. So that would be linear independence. And then for M times N matrix, so we just a review of spanning, because we're going to define what is basis, right? So basis require the sets to be linear independent as well as span Rn or whatever that you want to. So for spanning Rn, you want to make sure that there's a prefix position in every row. And if it's an N matrix, then you want to make sure that the good thing is an linear independent N set already would span Rn. Right. Another things, another things I want to say is if you have a set of vector is P, where P is greater than N, then they must be dependent. So it cannot be a basis. It would span Rn maybe, but it would not be a basis. So let's just introduce the definition of a basis. A basis is basically a set B1, B2, Bp in the vector space V. And it is a basis for H, okay, in the subspace H, so that they are linear independent. And also if you use this B1, B2, Bp and span something, is exactly H. So meaning this is the minimum set that would span a subspace in a vector space. So if your vector space is actually, if the subspace is the whole vector space like Rn, then we have a standard for Rn, we have a standard basis. Those are 1, 0, 0, 0, 1, 0. Like each column is in the identity matrix, so those are called standard basis. And then for polynomial, polynomial function of Pn, P highest degree n, then the standard basis are 1, t squared, all the way to t to power n. We proved that 1, t squares are independent, and you can, similarly prove the others, and they are all independent. Use the following procedures to check if a given set. I think there is something wrong here. So I cannot say that because of IRN. I would have to say I'll change the notes. Okay, let's check them. So how do I check if a given set H is a basis for Rn? So I should say B instead of H. Yeah, H is usually called a subspace. So you would put this set into the columns of the all vectors in H in B. Make the matrix A. Then you first of all you have to check that they're in independence, meaning you just do AX equal to 0 if it has only the trivial solution. So then they must be independent, right? Also, they cannot be linear combination of each other. In case you have two vectors, they cannot be linear combination of each other. If you are so lucky that you have n vectors and you're talking about Rn, then you can use IMT to see if the matrix A has prefix position in all row, or RREF to the identity matrix, right? Because by RMT, they are linear independent and also span Rn. So which is which is very important for being a basis. A basis has to be linear independent and be able to span Rn. Now, if you have too many vectors, they must be linear dependent, so it cannot be a basis. So this you can rule this out. But if you have too little vector, then it would not be able to span Rn because you cannot have a prefix position in all columns. Well, you cannot have a prefix position in all rows. So although if you are linear dependent, but you cannot have prefix position in all rows to span it, right? So yeah. So if you are too little, less than P, it cannot be a basis. It has to be exactly N. So let's do two examples. The first is have three vector, and we want to know if it can span Rm. We want to tell if it's a basis for Rm. So first is linear independent, and then the second is to check if it span R3, right? And because it is a 3 by 3, I can just use IMT can be used in one shot, because IMT is for n times n matrix. So make them into a matrix: 2, -2, 1, 1, -3, 2, -7, 5, 4. So do a RREF, see if it is row equivalent to an identity matrix. I already did in the matrix 2, 2, 1, 1, -2, 3, -7, 5, 4. It is REF is 1, 1 is row equivalent to 1, 0, 0, 0, 1, 0, 0, 0, 1 by IMT inverse matrix theorem. It must be the original matrix A must be linear dependent. The columns are linear independent, so I can show you. Here, columns of A form a linear independent set, and also the columns of A span R3, right? So, I would just do the condition number. So it's condition number E and also H, E and H. So we'll just say IMT E and H. Both of this okay, that means it's a basis for R3. So it's the same as the elementary matrix. If you use this, you can span all of R3. I don't have enough time to do B, so I'll do B in the next video.